Hello everyone. Hopefully you've had a good couple of days in class since fall break, and hopefully everyone had a good fall break. Sorry I am not there. I have been very sick with food poisoning from Guatemala, so I've been trying to get over that. I came in today and just couldn't even make it until 8 o'clock. So for your homework, you're going to do some of the notes. I know you guys have done 2 videos, one large video on Monday, a small video on Tuesday, and then you've done a reading quiz and then a long worksheet. So all of that kind of just covers this front page. So I'm going to go very quickly through this front page and then move on to the new stuff in the notes. So this is your new notes. This is page 1, and I'm going to go all the way up to page 4 or 5 today for your homework. Okay, so just a little bit about what you've learned in your videos is we learned about this thing called electromagnetic spectrum. An electromagnetic spectrum is just a gradient or a series of wavelengths and frequencies that's emitted from our stars and our sun. And these different types of radiation, we learned about alpha radiation, beta radiation, gamma radiation. They all have different what's called wavelengths and frequencies. But what's the same about all of them is they all move at 3.1 times 10 to the 8th meters per second, every single one of them. Let me zoom in here. And the reason why they all move this fast is because they're all some kind of spectrum of light. Even though we can't see it all, they still have the same properties of light, so they have the same speed as light. But they might behave a little differently. So light has both wave properties and particle properties. The wavelength is defined as from peak to peak of a wave. So this would be considered a wavelength. And this fancy letter here, lambda denotes is the variable for wavelength. And then we have something else called frequency. And frequency is how many different waves can pass through one point per second. So this is usually a really large number because waves move really fast. The units of frequency you might see are called hertz. That's one way. And if we're talking about radio waves, usually radio waves are expressed in hertz. Another way is per second. So either 1 over s, or a lot of the times you'll see people just put s to the -1. Anything to the -1 power means it's in the denominator. So these are the 3 different ways that you can see frequency. And frequency is denoted by the symbol nu, which is like a fancy V. Okay, so an equation we're going to use for this is the speed of light, which is denoted by the letter C. Why is it C? I don't know. Maybe because it means constant and this value never changes. So the frequency and the wavelength are all related to C, the speed of light. And we can write this equation C equals lambda nu, meaning every single time, no matter what the spectrum lies or where the spectrum lies, we will always have wavelength times frequency will always equals 3 times 10 to the -8th. So you will always know the answer to each question. You just need to figure out one of these variables. So, with that being said, with this equation, since this answer stays constant, if this guy goes up, then that guy must need to go down. So if this doubles, this needs to be cut in half in order for this answer to stay the same. Same thing, if my wavelength went down, then my frequency needs to go up to keep this answer the same. It always needs to equal 3 times 10 to the 8th meters per second. Speed of light. So we say that these are inversely related. If one goes up, the other will go down. And that was in your worksheet today. Here is the electromagnetic spectrum. It goes all the way from gamma rays to radio waves like AM and FM radio. Most of these rays you can't see. So for example, gamma rays, their wavelength from crest to crest is really short. And when it has a really short wavelength, that must mean it has a really high frequency. So its energy is really fast. So this guy has high energy, and these guys have low energy because their frequency is so big. So frequency, nu, and energy are directly related. And as you notice, if you have a really short wavelength, meaning this distance from crest to crest is really small, you have a really high frequency and you have a really high energy. If your wavelength is really long, that means you have really low frequency, so you have a really low energy. In this electromagnetic spectrum, you have what's called the visible light spectra, and it's this really small slither here. So you'll see this gradient starting with gamma rays, going all the way to radio waves. They have increasing wavelengths, and when they have increasing wavelengths, they have decreasing energy, and they have decreasing frequency. So violet has a certain wavelength. It's somewhere around 400 nanometers. Remember, nano is 1 × 10⁹. So violet, with a really small wavelength and a really high frequency, has the highest energy out of everything in the rainbow. Red has a really large wavelength, 700 nanometers, or 7 × 10⁹ meters. So red has a really long wavelength, which means it has a really low frequency and a really low energy. So, fortunately, this gradient follows the rainbow. It goes Roy, G, Biv, but this is in order of decreasing wavelength or increasing energy. So if we want to flip it, where we show decreasing energy, we just got to write it backwards. So now this is decreasing energy or increasing wavelength. So Roy G Biv is what you want to remember as far as increasing energy for electromagnetic spectrum. All right, let's solve some problems.